This is a video on arc length and surface area. What we'll start out with is arc length. So if we're given a curve for, say, an x between two numbers, then we want to find out, how do we find out what the length of that curve is? And then what we'll do is we'll take a curve, we'll revolve it around a line, like the x-axis, y-axis, or other line, and we'll say, well, what is the surface area of the solid of revolution about that line? So let's start out by looking at arc length. So if I have a curve, like so, and I kind of want to find the length of that curve between two numbers, we can't really use the distance formula immediately because it's not a line. And we only know how to find the length of a line, the distance between 2 points. But the good news is if that curve is a smooth curve, then if you zoom in really, really close, every curve looks like a line. And what we can do is we can find out what the distance is between those 2 points zoomed in. I'm not going to zoom in, but I'm going to show you what it looks like. So I'm going to take a bunch of points on this curve. And what I can do is I can approximate the length of that curve, say between 1 and 2, by looking at the distance from the first point to the second point to the third point, the third point to the fourth point, and the fourth point to the fifth point. Now we just got to remember the distance formula to find out what the distances are from one point to the next. So what we can say is that our delta L, we're considering these to be kind of small little intervals, and we'll call that delta L for the little change in length. Well, that's going to be the square root of the sum of the squares. So it's the square root of the change in x squared plus the square root of the change in y squared. Notice that if I cut this up into equal x intervals, I can just write delta x. On the other hand, the y values might change differently. Sometimes you'll have a big change, sometimes you'll have not so much a change in the y values. And that's why I wrote a little subscript, yi. So what we want to do is not just find the length of one little piece, but we want to find out what the total length is. Well, if we know the length of each of the little pieces, then we want to find the total length. Then that total length of the curve will be approximately equal to the sum of the lengths of each of these little pieces that are line segments. So I put a little sigma, and that's the summation I equals 1 to n. And that's approximately equal to the total length. So now I'm going to apply a little trick. I'm going to multiply top and bottom by delta x squared. When I do that, what happens is delta x squared over delta x squared is 1. Delta yi squared over delta x squared is delta yi over delta x, quantity squared. Since I divided by delta x squared, I need to multiply by delta x squared. But when I pull that out of the square root, I get a delta x. And the good news is this should look a little bit familiar, because I don't want just an approximate length, I want the exact length. And to get the exact length, instead of saying, well, I'm going to cut this up into 4 pieces, well, I could try 400 pieces or 4 million pieces. But even better is I could take the limit as n goes to infinity. So I'm going to cut this up into an approximately infinite number of pieces and then add up every piece. And this is what calculus is all about. So L is equal to, it's no longer approximately equal to, but it's equal to the limit as n goes to infinity of the summation of the square root of 1 plus delta yi over delta x, quantity squared, all times delta x. And this looks familiar. When you have a limit of a sum of stuff times delta x, that's an integral. So we can say that the length of the curve, by definition now, is equal to the integral from a to b, where a is the starting value and b is the ending value for x, of the square root of 1 plus the derivative of the function. Sometimes we call that f prime of x squared dx. And that's how we're going to find arc length of a curve. So now let's look at an example. Let's see if we can find the arc length of the curve y equals x squared for x between negative 1 and 1. So all I do is I put it into the formula. We need to find y prime. Well, y prime is 2x. The square root of 1 plus y prime squared is the square root of 1 plus 2x quantity squared, which is just 4x squared. So we know that our length is equal to the integral from negative 1 to 1, because that's what a and b are, of the square root of 1 plus 4x squared dx. Okay, this is not an impossible integral, but this is a really rough one. So we could do it. You may have to wait until you learn about advanced techniques of integration, but let's do it the easy way. And hopefully y'all know the easy way, and that is put it into a computer. And I popped that into a computer, and what I got was approximately 2.2956. And that is the arc length of the curve y equals x squared for x between negative 1 and 1. Pretty much every arc length is going to look the same. What you're going to do is you're going to find the derivative. You're going to square that derivative. You're going to pop it into the square root of 1 plus y prime squared formula, and then just integrate from a to b. Because of the square root of 1 plus y prime squared, most of the time this is going to be an impossible integral. So calculators or computers, I like computers, are very good for calculating integrals for as many decimal places as you feel like. All right, so now let's look at the surface area of revolution. So what I have here is a curve, and we're going to go between 0 and 2, for example. And what we want to do is we want to revolve that curve around the x-axis. And we're going to get a solid when you do that. And we want to find out what is the surface area of that solid. So in order to do that, it's very similar to the arc length idea. What I'm going to do is I'm going to take kind of two consecutive points. I'm going to take this first point, and I'm going to revolve the first point around the x-axis. So you can see I've revolved the first point around the x-axis. I'm going to take that second point and revolve it around the x-axis also. I'm going to connect the other side so we can kind of see what we've got. We have this interesting figure where pretty much it's not quite a cylinder, because cylinders go straight up from the bottom. This is called a frustum. And what that means is you have two circles. One's bigger than the other typically, and one on top of the other, and then they're connected. And that makes it a frustum. So we're going to do kind of the same idea. What we're going to do is we're going to find the surface area. So the surface area of the frustum, if you remember, the surface area of a cylinder was 2 pi RH. Very similar, but instead of measuring the height, we measure the length of the line segment from one point to the next point. So what we could say is this little delta surface area is equal to 2 pi r times delta length. Now let's just put things together. That's going to be 2 pi r. We've already found out what delta length was. That we did in the last example when we found the arc length. We found out that delta L was a square root of 1 plus y prime squared times delta x. Now we just got to find r, but r is quite easy here because r is going to be the distance from the x-axis to the curve. And that distance is a vertical distance. So that vertical distance is just f of x. And then we do the old add them all up, take a limit as n goes to infinity of the summation of 2 pi times f of x times the square root of 1 plus f prime of x quantity squared, delta x. And that'll give us the surface area. And once again, when you have a limit of a sum of a function times delta x, that's an integral. So there we have the big formula for the surface area. The surface area is equal to 2 times pi times the integral from a to b, that's the left to the right, of f of x times the square root of 1 plus f prime of x quantity squared dx. So now let's go ahead and apply this formula to an example. So the question is, find the surface area of the solid that is formed by revolving the curve y equals the sine of x for x between 0 and pi about the x-axis. So as we've been doing for a while, the first thing you want to do is draw the picture. We have y equals the sine of x for x between 0 and pi. So there's our picture. You should all know what y equals the sine of x looks like. There it is, x between 0 and pi, a little more than 3, and we get this beautiful curve. Then what I'm going to do is I'm going to take a little piece of it, like so. I'm going to take the 2 points, and I'm going to revolve them around the x-axis. And there's the frustum. Always a good idea. You should always have your picture, and you should get the frustum, and that reminds us how to get this surface area. So now we know that the surface area will be 2 pi in the formula times the integral, x goes from 0 to pi, so integral from 0 to pi. Then it's f of x, well, f of x is the sine of x, times the square root of 1 plus, now the derivative of the sine of x is the cosine of x. Square that, and you get cosine squared of x, and then dx. Again, this would be a tough one to do by hand. I am going to use a computer, and when I use my computer, I got about 14.4236 for the surface area of revolution when you take the sine of x, y equals the sine of x, revolve it around the x-axis for x between 0 and pi. So now let's revolve around the y-axis, and let's see what happens. So here's a curve. And what we want to do is we want to revolve around the y-axis. It's going to look very similar. The first thing I do is I say, well, what if I have a piece of that? I'm going to take those 2 dots, the 2 endpoints of my line segment. I'm going to revolve that line segment around the y-axis. And there's the picture, and what do you know? We got a frustum again. And we know how to find the surface area of a frustum. The surface area of a frustum is 2 pi r times delta L. Nothing's changed. Everything's the same. So we know that's 2 pi r times the square root of 1 plus y prime squared delta x from before. So now we just got to look at r. Turns out r is really easy. Unlike before, when you measured it and you got a variable and you had to switch it around, now we just measure it and we say, well, it's the distance from the y-axis to the point on the curve. Well, that's a horizontal distance, and since we're going dx, horizontal distances are just x. So we could say the surface area, when you revolve around the y-axis, is equal to the limit as n goes to infinity of the summation of 2 pi x, because that was the radius or the distance between the y-axis and the curve, times the square root of 1 plus f prime of x, quantity squared, delta x. So the formula for finding the surface area the region formed by revolving a curve around the y-axis is 2 pi times the integral from a to b of x times the square root of 1 plus f prime of x squared dx. So now let's look at an example. The example is, find the surface area of the solid that is formed by revolving the curve y equals e to the 2x for x between 0 and 1 out the y-axis. So again, we draw the picture. Here's our curve. We have 2 points. We revolve each of those points around the y-axis and then connect, and there's our frustum. So now that we have our frustum, we can find the surface area by using the formula. So the surface area is equal to 2 pi times the integral from 0 to 1, because x goes from 0 to 1, of x times the square root of 1 plus, now we find the derivative. The derivative of e to the 2x is 2 times e to the 2x. That's the chain rule. So it's the derivative, 2 times e to the 2x, quantity squared, dx. And again, you definitely do not want to do this one by hand. Instead, I put this into my computer, and I got 40.8075 as the surface area of the solid of revolution as you revolve y equals e to the 2x for x between 0 and 1 about the y-axis. So let's do one more example. Let's revolve around another line. The question says, find the surface area of the solid that is formed by revolving the curve y equals the square root of x. X goes between 0 and 4 about the line y equals 3. So here's a picture drawn. We have y equals root x. I took a couple points. I revolved those points around the line y equals 3. And I get a frustum. I need to find out what the surface area is using the area of the frustum formula. So we know that the surface area is 2 pi times the integral from a to b times r times L dx. So in this case, we have our 2 pi times the integral from a to b. Notice that the radius is a distance from the axis of rotation to the curve. We know that the distance from the axis of rotation, the line y equals 3, to the x-axis is 3. That's too much, so we need to subtract off the distance from the curve to the x-axis, which is f of x. So our r will be 3 minus f of x. Then we multiply by the square root of 1 plus f prime of x quantity squared, because that was the formula for length, dx. So now let's plug in. We know that x goes from 0 to 4, so we have 2 pi times the integral from 0 to 4. We have f of x was a square root of x, so we get 3 minus root x times the square root of 1 plus. Now we take the derivative. The derivative of the square root of x, remember that's x to the 1/2, will be 1/2 x to the negative 1/2. And if you write that back in roots, you get 1 over 2 root x. And if we square that, 1 over 2 root x squared is going to be 1 over 4x dx. And once again, I'm going to use my computer to find this integral. And what I got is approximately 51.4129. And that is the surface area of the solid of revolution when we revolve the curve y equals root x between x equals 0 to x equals 4 about the line y equals 3. And that's about all I have to say for finding the arc length and finding a surface area for a solid of revolution. So thank you for watching this video.